Hello, welcome to the second part of the presentation. We're going to talk about three colorations of knot projections today. So what are the three colorations? We can consider them as a kind of function that assign each of the arc with a specific color. And the fact that they are a special kind of coloration means that we have to satisfy a set of properties that proper we'll define later. And for the projection, we will start with the arcs. And let's review a little bit about the arcs. So the arcs are really just a kind of path that is maximal, which goes from any undercrossing to another undercrossing. Basically, we can dissect this trefoil into three arcs in this case. For this 8 symbol, we have only one arc. It's not hard to visualize that if we want to color for like every arc, we give that a specific color. And for the sake of simplicity, in this presentation, we will assign them with numbers, also color code them for visualization. And for every crossing, we basically send this set of arcs in projection to a set of color values we define by ourselves. In general, we take n equals to 3, which is a very special and interesting case, but more generally, the coloration number can be as many as you want. It's easy to see that if we don't limit this number of colors, then the value for total number of possible colors will, total number of possible colorings will equal to number of colors to the power of number of arcs. And this is generally very large. This is also the case for n equals 3, which give you something like this. Still a very large number, and I will argue that maybe that's not really helpful, because just usually when you have a very large number, it's hard to examine the property underneath. So let's go to place some restriction on that to make sure that this value is not so large. We want to make sure that the only coloring we consider are proper colorings, and this will significantly cut down this number. Why? Because we only allow for each crossing to involve 3 different colors or 1 color. So it basically limits a lot of possible colorations. Now let's take a look. Is this coloration proper? We can examine these 3 crossings and see, hey, all of them are within type 1. So yes, this is a proper coloration. How about this one? Well, this is from type 2, isn't it? So yes, this is still a proper coloration. Well, this Celtic knot. This Celtic knot has a lot of good coloration points. However, it does have 2 naughty colorations, which result in a not proper knot coloration. So, sorry, this is not a very proper coloration. Now we'll see for some of the knots it's really hard to make interesting proper colorations, and we can determine that actually using an algorithm we defined. So using Erica's encoding, we have now this set of crossing represented as each of the blocks. We can convey this color information in the graph by assigning the colors on the corner of those blocks or squares. And for each of the square, we simply need to check that all of them are either within these 2 kind. And also, just for the sake of sanity check, we want to make sure that every edge here connect to the same kind of color to make sure that every arc contains only 1 color. Using this algorithm, we can drastically speed up this checking method, and as we will see later on, it will also help us compute proofs using computers, which is pretty cool. And because of this nice things about this 3 colorability, we will always assume proper coloration whenever we talk about the colors in the future. So now let's take a look at something interesting. We will say this trivial coloration happens for every possible knot projection. Just assign everything with a 1 color. And we will always have some kind of trivial coloration. That's not very strong. Instead, the non-trivial 3 coloration is much more interesting because some of the knot, for example, the circle, will never admit any non-trivial 3 coloration. For this trefoil, though, we do have one. If you distort this trefoil a little bit, you will still get one non-trivial 3 colorations. So we will now start to see, hey, maybe these two are connected somehow. Their triviality in 3 coloration has something in common with their knot correspondence. In this one, it's still the case. You can never color this non-trivially. So we start to have the suspicion that maybe the projections are actually tied with their non-triviality of 3 colorations, and that turns out to be exactly true. The coloring theorem we have proved in our research tells us that the colorability, if we talk about only non-trivial colorings, are not level invariant. What do I mean by that? Basically, you can apply this theorem to prove that two knot are not the same. What you can do is to prove that A has a non-trivial 3 coloration, B does not have one. Then you have basically proved that A and B are not the same knot. I know this is confusing wording, and just take a look at the example below. Oops, sorry about that. So the proof of this is we can examine this one and say, hey, this pentafoil, do you have any coloration at all? This must be true, because if we have any more than one colors, then they must meet at one point. This determines that we have this crossing, and this must be type 1. All of them within the different colors, resulting in this arc to be in color 3. Looking at this crossing, we'll see that this arc must be color 3 as well. There we have a contradiction, because now it's impossible to color this one properly. So by symmetry, we can see it's impossible to color this one. No non-trivial. And this one has non-trivial. Using this idea, we prove that these two are not the same. Although this is kind of abstract so far, we have to concrete it by proving the theorem. And we do have the proof. However, for the interest of time, we won't present the entirety of that. Rather, I'll talk about the overarching ideas, which is basically we define something called coloring isomorphism. For each of these two colors, these two as well, they are isomorphic. Because as you can examine the way we color them, they are very similar. Basically, you can use a permutation of colors to get one coloring to another one. Then it's natural to think that for each of the knot, we can figure out how many ways are there to color them in distinct non-isomorphic ways. These are the 5 classes of the coloration we can place on this knot, and we will assign this counter function the value n. Determining the value n is usually tedious, but for the sake of proof, it's actually pretty helpful, because for everything that only have a trivial coloration, this value will be 1. For everything that has at least one non-trivial 3 coloring, we'll have this value greater than 1. For example, this trefoil. Now, we simply need to check that for every Reiter-Meister move, the value n won't change. Basically, if you take this knot projection and do some Reiter-Meister move, it will still have the n value being 1. Basically, this proved that our 3 coloration triviality is tied deeply in the knot equivalence. And for the people who are interested in this, I have posted a PDF here, and you can examine the proof on the case of Reiter-Meister move type 2. We have more in the paper, but I think this is convincing enough. Thank you very much for your attention. After this part, we are going to talk about binary sum, which is another very interesting aspect of the knot understanding.